Okay, the first question of part 3, and that is, I think, fill the blank space. The least upper bound of the set minus 1 the power of n plus 1 over n whenever n is an element of n is, we know that for n to be odd and even natural number, we have different values for this thing. For odd n, minus 1 the power of n plus 1 over n could be minus 1 plus 1 over n, because minus 1 to the power of any odd natural number is minus 1, which is less than or equal to 0. But for n even, minus 1 the power of n is always 1. That is, minus 1 to the power of any even natural number is 1 plus 1 over n. So that the maximum occurs for even n. Largest one will be whenever n is equal to 2. So that 1 plus 1 over 2 is 3 over 2. Any elements of this one, or simply whatever n is odd or even, always less than or equal to that of this one, that's simply 3 over 2. So that's 3 over 2 is the maximum element of this expression. So therefore n is equal to 4. 1 plus 1 over 4 is 1.25. As we have such a value here, which is strictly less than that of this one, that's simply 3 over 2. Therefore, whenever n tends to that of infinity, for even natural number, 1 plus 1 over n will tends to 1. That is, this could be tends to 0. 0 plus 1 will be 1. Therefore, but this one, that simply 3 over 2 is the maximum element which is obtained whenever n is equal to 2. That is the first even natural number. All the other values are simply greater than that of all the other values. Therefore, the least upper bound, that is 3 over 2, is one of the possible upper bound of this one. And the least, or simply the smallest upper bound of this could be 3 over 2. And therefore, the least upper bound for this set could be 3 over 2. Next, that is question number 2. We have let z is equal to the set containing x an element of z whenever the absolute value of x is less than or equal to 3, and r is equal to the set containing the order for x, y such that x squared minus y is less than or equal to 2b, a relation on A. Then the range of r inverse is blank. We know that obviously from here we have set A here, the relation r which is defined over here, so that the domain of the given relation is the range of its inverse, or the domain of its r inverse could be the range of the original function. We know that is the absolute value of x less than or equal to 3 means, since x is an integer, it could be minus 3, minus 2, minus 1, 0, 1, 2, and 3. That is in between minus 3 and that of 3 whenever x is an integer. And therefore, the relation that is r could be given to be this one, that's simply the set of order of x, y such that y is greater than or equal to x squared minus 2. Then the relation that simply r inverse could be, the inverse of this relation could be the set x, y such that whenever x, y is an element of r, and the sense of that of order pair, that means therefore range of r inverse is equal to domain of r, or a set of x values in R. That means for each x an element of A, find y an element of A such that y is greater than or equal to x squared minus 2. Therefore, the smallest x squared minus 2, when x is equal to 0, it is minus 2, so that y can be minus 2, minus 1, or simply any of this. And then whenever x is equal to plus or minus 1, 1 minus 1 could be minus 1. It works, that's because it is within A here. Again, whenever x is equal to plus or minus 2, we have, that is if we substitute to 4x within this function, we have 4 minus 2, that's simply positive 2. Positive 2 is within the given set, that's simply A is again, so that it works again. Whenever x plus 3, where x equal to plus or minus 3, we have 9 minus 2, which is 7, but 7 is not within A here, so that no y A satisfies. So x can be minus 2, minus 1, 0, 1, and 2. Implies range of R inverse is equal to minus 2, minus 1, 0, 1, and 2. So that the answer for this one could be a range of R inverse, which is the domain of R. That means domain of R, which is equal to minus 2, minus 1, 0, and 0, 1, and 2. Next question, question number 3. Given a polynomial function p of x, x cubed minus 2x squared plus x minus 2 with root x equal to I. Then the other non-real root is, that is the other complex root. That means, we know that using complex conjugate theorem, complex root of a polynomial with real coefficients come in conjugate pairs. If I the root, then it is complex conjugate, that is minus I is also it is root, so that the non-real root is minus I, because just we are informed that I is the root of this polynomial function, so that it is complex conjugate, which is minus I must also be its root, so that the answer could be minus I. Okay, question number 4. If the LCM of A and 30 is equal to 1350, then A is equal to, using that of prime factorization, I think prime factorization is applicable here. Let us try to factorize 30 as using its prime factors, 2 times 3 times 5, and this one that's simply 1350 could be 2 times 3 to the power of 3 times 5 squared. Then we know that in order to find the LCM of the given function, I mean the two numbers from their prime factors, we must take the highest power of all common prime present, and also the other non-zero primes with the highest exponents also must also be taken. Therefore here, the LCM of this one, that is n, that of 3 is given to be that of this one. This could be taken from the prime factors of n, that of 30, with the highest exponent from the prime or simply common primes and others. Sorry. So A must contain, that is simply 3 to the power of 3 and 5 to the power of 2, but may or may not contain 2. 2 may or may not be an element of the prime factor of this one, that is A, so that we have to consider cases. The first case, when A contains 2, then A could be 2 times 3 cubed times 5 squared, which is equal to 1350. And the other could be the second case, that is whenever A is not doesn't contain 2, then A could be 3 cubed times 5 squared, which is 375. Therefore, the answer for the possible value of A could be either 775 or 1350. Question number 5. The imaginary part of 1 plus I over 1 plus radical 3 I is, and just as usual, in order to know the real and imaginary part of the given complex number, we must first solve or simply write it in the form of A plus I times B, that is in standard form. In order to find the standard form of this one, we have to multiply both denominator and denominator by the complex conjugate of the denominator, that is 1 minus radical 3i. So when we do this, 1 plus I, that is the denominator of this fraction, times 1 minus radical 3i, which is the complex conjugate of this one, over the product of this complex number 1 plus radical 3i, and its complex conjugate could be 1 squared plus radical 3i squared, which is equal to this expression. So that 1 plus radical 3i plus I into 1 plus radical 3 over 4, since minus the square root of 3 times I squared is equal to plus positive 3 radical 3. Then we have the complex conjugate, or the complex number, that is this will be, that is simplified form will be 1 plus radical 3 over 4 plus 1 minus radical 3 over 4. Therefore, the imaginary part of this complex number could be 1 minus radical 3 over 4, which is the coefficient of the imaginary number I. Okay, question number 6. Let f of x equal to minus 5x plus 3 and f composite of g of x is given to be 5x squared plus 10x plus 3. Then we are asked just to find g of x. We are given f of x, a linear function, and composition of this function f and the unknown function g to be this quadratic. So using the rule of that of composition function, we know that f composite of g of x equal to f of g of x, but g of x is not known, but f of x is given to be, and that is the input that is negative 5 times the input that's simply x, which is g of x in this case, plus 3 is equal to, it is equivalent to this one, which is 5x squared plus 10x plus 3. And therefore, minus 5 times g of x plus 3 is equal to 5x squared plus 10x plus 3. Therefore, taking this one to right side, we have minus 5 times g of x equal to 5x squared plus 10x. Then when we divide in order to obtain an expression for the unknown function, that's simply g of x, let us divide both sides of this equation by the coefficient of this one, which is negative 5. Therefore, we have g of x equal to minus x squared, which is 5x squared over minus 5, which is minus x squared, and 10x over minus 5 could be minus 2x. So that's the answer for this one could be g of x equal to minus x squared minus 2x. You can check by taking f composite of g of x whenever g of x is this one to be 5x squared plus 10x plus 3. And next question. Question number 7, if twice of z minus I times z bar is equal to 3 into 3 minus 5i, then z is equal to blank. So by letting z to be the form of z in standard form to be a plus bi, then a z bar could be this thing. Then when we substitute this one over here, we'll obtain 2 into 2 plus, a plus bi minus I into z bar, that is a minus pi, is equal to 9 minus 15i. 9 minus 15i, that when I distribute this one over here, 3 times 3 is 9. 3 times minus 5 is minus 15. Then distributing 2 over here and distributing minus I over a, the complex conjugate of z, which is a minus pi, we all obtain 2a plus twice of pi minus I times a, which is ia plus I times this one, which is negative times negative is positive, that is I squared b, which is 9 minus 15i. Then twice of a plus twice of pi minus I minus b, because I squared is minus negative 1, so that it becomes I squared b becomes minus b, which is 9 minus 15i. Then collecting the real and the complex, that's simply the terms without I and I together. We have 2a here minus b, that is twice of a minus b plus. Factoring I the common factor, we have 2b minus a is equal to 9 minus 15i. Then equating the real and the imaginary parts together, we have the real part, because two complex numbers are said to be equal whenever they have the same real part and the same complex part. So that the real part of the first one, that is twice of a minus b minus 2b, identical with the real part of second given complex number, that's simply 9. And the imaginary part of this, 2b minus a, must be identical with the imaginary part of this one, which is minus 15. Then solving this system of linear equation, we have b is equal to twice of a minus 9. Substitute this here, and we can obtain a to b, this one, that's simply 1. Then whenever A is 1, B could be, in order to find B and B, we have to select either of these two and substitute 1 in the place of A within the selected equation. So that B could be twice of A. That simplifies, select the first one. That means 2 times 1 minus 9, which is equal to 7. Therefore, Z could be, if you substitute A and B in the place of here, Z could be 1 minus 7i. So the answer is, the last answer for this question will be 1 minus 7i. Question number 8. The rational root of f of x is given to be 5x to the power of 4, or simply this expression. The rational root of this function. We know that we're using rational root tests or by rational root theorem. Possible rational roots are the factors of the constant term, that's simply 1, over the possible factors of the leading coefficient, because already the coefficients of the given the terms of are over integer, that's simply integer, so that using that of rational root test, if this function has a rational number which is a root or simple rational root, so that the denominator must be possibly one of the possible factors of the constant term, and the denominator must be possible factors of the leading coefficient, which is 5. So we know that the factors of 1 are plus or minus 1, and the factors of the leading coefficient, that simply 5, will be plus or minus 1 and plus or minus 5. So that the rational root of this function, if it has, must not be out of the combination of these factors. So that the possible factors could be plus or minus 1 and plus or minus 1 over 5. Then, in order to test for example, that's simply for 1. That means which is obtained by taking the combination of 1 from the first and 1 from the factors of 5, or minus 1 and minus 1. We have f of 1 is equal to, this is already 0. So that since f of 1 is equal to 0, one of the possible rational root of this function is 1. Similarly for the other, that's simply f of minus 1 is positive 24, which is different from that of 0, so that x equal to minus 1 is not the rational root of this polynomial function. F of 1 over 5 is 96 over 125, can check it, which is non-zero. Hence, x equal to 1 over 5 is also cannot be the rational root of this polynomial function. And lastly, f of negative 1 over 5 is 216 over 125, which is also non-zero here. Therefore, x equal to negative 1 over 5 is not its root. Therefore, the only root of the given polynomial function could be that is x equal to 1. Okay, the last question, that is question number 1, that is the last part. Find the root of z cubed is equal to minus I. So in order to find the root of extraction of root of complex number, that means write minus I in polar form. That is, first we have to write minus I in polar form, and the polar form of minus I could be cosine of negative pi over 2, because the argument of this one, that simply could be minus pi over 2 plus I times sine of negative pi over 2, or minus I could be, in using that of Euler form, is the power of minus I times pi over 2. Then z is equal to r times e to the power of I theta. Then z cubed could be r cubed times e to the power of 3 theta. It's again Euler formula, which is e to the power of minus pi over 2. Minus I pi over 2. So r cubed is 1, because here r is equal to r cubed. That's simply we have 1 here. And then 3 theta is equal to negative pi over 2 plus, that is 2 pi k, wherever k is equal to 0, 1, and 2. Then theta is equal to minus pi over 6 plus 2 pi k over 3, whenever k is again within this one either of these three values. Therefore, for k is equal to 0, we have theta is equal to only this becomes 0 and only minus pi over 6 will be left. So that the denote could be cosine of negative pi over 6 plus I times sine of negative pi over 6, which is equal to radical 3 over 2 minus 1 over 2i. So that this is one of the possible root of this expression or simple equation. Secondly, for k is equal to 1, pi is equal to negative, that is this expression, this theta could be minus pi over 6 plus 2 pi over 3, which is equal to pi over 2. Therefore, z1 could be cosine of pi over 2 plus I times sine of pi over 2, which is I, because cosine of pi over 2 is 0, so that this is already cosine of pi over 2 is 1, therefore 1 times I could be I, therefore the second root of this polynomial, equation is I. And lastly, for k is equal to 2, this expression again becomes minus pi over 6 plus 4 pi over 3, which is equal to 7 pi over 6. Therefore, the data could be cosine of 7 pi over 6 plus I times 7 pi over 6, which is equal to negative radical 3 over 2 minus I over 2. Therefore, the values of z are negative radical 3 over 2 minus 1 over 2i, and negative radical 3 over 2 minus 1 over 2i. Okay, question number 2. Given the function f of x equal to x squared, the rational function square plus 5x plus 4 over x squared minus 1, that we are asked just to determine the domain of the given function. We know that the domain of the given function is the set of real number without the set containing the denominator, that is x squared minus 1 is equal to 0. So that the denominator x squared minus 1 is equal to 0 whenever x equal to plus or minus 1. Therefore, the domain could be R without the set containing minus 1 and 1. B, the intercepts of this function, that is, we have two intercepts, x-intercept and y-intercept, so that the x-intercept will be obtained by letting y to be 0, that is x squared plus 5x plus 4 is equal to 0. For that, we have this one, then x equal to minus 4, or x equal to minus 1, but as x equal to minus 1 is not within the domain of the given function here, because it is the domain is that this rational function is R without minus 1 and positive 1, so that the only x-intercept of this function, the rational function, could be minus 4, 0. And its y-intercept will be, the y-intercept will be obtained whenever by letting x to be 0, so that f of 0 could be already 4 over minus 1, which is equal to minus 4. Therefore, 0 minus 4 will be exactly the y-intercept of the function. And next, the asymptote of the given rational function. The asymptote could be a vertical asymptote, so that the function that simply wherever denominator is 0, but denominator is non-zero. So at x equal to 1, denominator is 10, which is non-zero, and that's the denominator is 0, so that the vertical asymptote could be x equal to 1. But at x equal to minus 1, the denominator is also 0. Therefore, the x equal to minus 1 can never be the vertical asymptote, rather it. Question number 2. We are given the rational function, that is f of x equal to x squared plus 5x plus 4 over x squared minus 1. And we are asked just to determine the following. The first one is the domain of the given function. We know that the domain of a given function is the set containing a set of real number without the set, the element that can make the denominator, in this case x squared minus 1, 0. And denominator x squared minus 1 is equal to 0 for x equal to plus or minus 1. So that the domain of the given relation is R without the set containing minus 1 and positive 1. The next one, that's question number B. the intercept, that is x and y intercept of this rational function. We know that the x-intercept is set the numerator is equal to 0 whenever x plus 5x equal to 0, which implies factorized form of this numerator could be x plus 4 times x plus 1. They hit 0 whenever x equal to minus 4 and x equal to minus 1. But in this case, x equal to minus 1 is not within the domain of the given rational function because it's already without minus 1 and the positive 1. So that the only x-intercept of the given rational function could be minus 4, 0. And its y-intercept will be, that is, y-intercept is whenever x equal to 0 or simply f of 0. So f of 0 is equal to 4 over minus 1, which is minus 4. Therefore, 0 minus 4 will be the y-intercept of the given rational function. The next one, the asymptote of the rational function. The vertical asymptote could be whenever the denominator is 0, but the numerator is 0, that is x is equal to a certain real number is said to be vertical asymptote of the given rational function whenever the denominator is 0, but the numerator at that point is non-zero. Therefore, at x equal to 1, the numerator is x plus, that's 1 plus 5 plus 4, which is 10, which is non-zero. So that the vertical asymptote, one of the possible vertical asymptote of the given rational function could be x is equal to 1. But at x equal to minus 1, the numerator is also 0. The denominator is also 0, so that's x plus 1 will be the factor for both the numerator and the denominator of the given rational function. Therefore, x equal to minus 1 cannot be the vertical asymptote. Rather, the rational function will have a whole at minus 1. The horizontal asymptote could be, because we know that a rational function will have a horizontal asymptote whenever either the degree of the numerator is less than that of the degree of the denominator, or the degree of the numerator and the denominator are equal. In this case, the degrees are equal, so that the horizontal asymptote will be the line which passes through the quotient of the leading coefficients of the two polynomial functions. Therefore, the leading coefficients are, in both cases, they are, that is, the leading coefficients are, the is also 1, the second, the denominator is also 1. Therefore, the horizontal asymptote will be 1 over 1, which is y is equal to 1. It doesn't have any oblique asymptote because the rational function will have an oblique asymptote whenever the degree of the numerator is greater than that of the degree of the denominator by 1. Just to calculate the whole at x equal to minus 1, first we have to simplify the given rational function. The simplified form of the given rational function is x plus 4 over x minus 1, but the equivalent to that of the rational function whenever x is minus 1, different from that of minus 1. That means, so that at the simplified function, x equal to minus 1, that is, we have negative 3 over 2. Therefore, the point minus 1 minus 3 over 2 will be the whole for the given rational function. That means the given rational function will leave a whole at this point, that is at minus 1, negative 3 over 2. Then combining this information, the rough sketch of the given rational function will looks like this. It has a vertical asymptote at x equal to minus 1, this vertical asymptote. The y-intercept is 0 minus 4 here. The x-intercept is minus 4, 0 here. And the horizontal asymptote is the line that is above the red line, that's simply the x-axis, which is y is equal to 1 here. And the property of the graph near the vertical asymptote and the originally generally the asymptotes will be at the vertical asymptote x equal to 1 whenever x approaches the vertical asymptote from the right side, from this side, that's simple in this direction, the value of the function will tend to that a very large positive number, that's positive infinity. Similarly, on this side, when x approaches to that of positive infinity, the graph will approaches the horizontal asymptote that's simply y is equal to 1 from above. So that is the property of the graph of the given function to the right of the vertical axis. The vertical asymptote, I mean. And to the left of the vertical asymptote, when x approaches the vertical line that is x equal to 1 from the left side, so that the limit of this one, that's simply whenever x approaches positive 1 from the left side, the functional value of this rational function will tend to negative infinity like this. So that the graph of the given function near to the vertical asymptote from the left side looks like this. And from whenever x tends to that of negative infinity, it approaches so simply, it intersected the vertical axis at 0, -4. Then it goes on in this pattern. It will leave the hole that's simple at -1, -3 over to here. They hit the hole, and it intersected the horizontal axis that's simply the x-axis at -4, 0, and it approaches the horizontal asymptote, that is y is equal to positive 1 from below. So that roughly the graph of the given rational function x squared plus 5x plus 4 over x squared minus 1 looks like this. Okay, thank you. That's all.